Hello, today's video is on Chapter 3, Section 4, which is linear programming. Before we get into linear programming, there's a couple of things that we need to talk about and review. First is how to graph a system of inequalities. When we look at our first inequality, it's not in graphing form, so we're going to change it into graphing form by moving that x over. So we've got y is less than a negative x minus 1. We start down at our y-intercept of negative 1. With the slope of a negative x, which is a negative 1, we go down 1, right 1. You want to make sure that you are covering the entire region, and it is extremely important that you have every dot that's going to go from left to right. And since it's less than, we are going to have a dashed line, because that line is not going to be included. We go to our second inequality, x is less than 2. That is going to be a vertical line at 2. And again, this one is going to be a dashed line because it's less than. And our last one is y is greater than or equal to a negative 1. That's a horizontal line at negative 1. And that one is going to be solid because it's greater than or equal to. Now we need to find the common ground between those three equations. Since I went less than the blue line, I want everything below the blue, which means everything above it is no longer fair play. That's not going to be part of our answer. Then we want x is less than 2. So now not only do I want everything below the blue, I want everything to the left of the red. So right now, below the blue and left of the red is going to leave me just with this piece inside of here. And then last, I want above the negative 1. So my feasible region, or where those three are all overlapping, is going to be right there. That's the only piece that's going to be shared by all three graphs. So a new terminology for you is optimization. Optimization is finding the maximum and or minimum value of some quantity. And this is going to be one of those, when am I going to use this kind of stuff? The optimization is used a lot by companies. So finding the maximum or minimum value of some quantity. And as I just said, one type of optimization is linear programming. And linear programming is all what 3.4 is about, and companies use this kind of optimization process to determine what their max profit could be or what their minimum cost should be. Because we know in companies, it's all about the money. You want to maximize your profit and you want to minimize the cost that you are sending out. In linear programming, an objective function is subject to a system of inequalities called constraints. The graph of the system of inequalities is called the feasible region. So you're going to graph all of your inequalities the same way we did in our warm-up problem. Those are what we would call the constraints. So those three inequalities from the warm-up, those would be the constraints. You would have a separate objective function that you would look at to compare the feasible region, which is the shaded part of your system of inequalities. Alright, so there are 3 steps to evaluating linear programming. Step 1 is to graph the feasible region. And as I said before, the feasible region is simply graphing a system of inequalities with shading their common ground. After you've graphed the feasible region, you are going to plot the coordinates of that region. And we'll talk about that more once we get to our first example. Once you have the graph of the feasible region and you've plotted the important coordinates, you're going to plug the x and y coordinates from step 2 into the objective function, yes. Okay, so you graph it, you find your coordinates, then you take those coordinates and plug it into the objective function. If the feasible region is bounded, then the function will have a max and a min. That means it's enclosed in all areas. If the feasible region is unbounded, then the function will only have a maximum or a minimum. It'll only have one or the other. It won't have both. Alright, so let's put this into an example. It'll make much more sense. So we have our objective function, c is equal to 2x plus 4y. We're not going to use that until step 3. We have our constraints. Our constraints are our three inequalities in this case. So we've got x is less than or equal to 3. That means I have a solid line and a vertical line at 3. And then we have x plus y is greater than or equal to 3. We move our x over, so we've got y is greater than or equal to a negative x plus 3. We start up at our y-intercept of 3. We have a slope of a negative 1, so we go down 1, right 1. We see that that's going to intersect our blue line. We're going to keep going. We're going to go in the other direction as well, up 1, left 1. And that's going to be solid line as well because it says it's greater than or equal to. Remember, using your ID will give you nice good straight lines if you don't have a ruler. And our third equation, we move that 2x over. Then we have to divide by a negative 3. And remember, inequality, when we divide by a negative, we've got to flip that sign so it's less than or equal to a positive 2/3 x plus 3. So we have a y-intercept at 3 again. Our slope of 2/3, so up 2, right 3, up 2, right 3, up 2, right 3. We could also go down 2, left 3, down 2, left 3, down 2, left 3. And again, we are going to have a solid line because it's less than or equal to. Now for the hard part, finding that feasible region where it's going to match up for all of our inequalities. We went less than 3, so we cut out everything to the right of our vertical line. And then we went above red. So now we have only this region in here. And then our last inequality, we went below green. So the feasible region, in this case, that's going to satisfy all three inequalities, that little triangular shape right there. That is step 1, finding the feasible region. Step 2 is finding the coordinates. And what the coordinates are is the vertices of the feasible region. So every point that the feasible region creates become your vertices. So this one would be 3, 0. This one would be at 3, 5. And our last one at 0, 3. Okay. So step 1, we graphed our feasible region, simply graphed our system of inequalities. Step 2 is finding the coordinates of that feasible region, which is just the vertices created with the feasible region. And our last step is plugging those points into our objective function. So this is where our objective function comes into play. We've got c is equal to 2x plus 4y. And we've got 3 points we've got to check here. So we've got 0, 3. We know that this is our x and this is our y. So we've got 2 times 0 plus 4 times 3. 0 plus 12. We've got a value of 12 here. Our second point, we've got 3, 0. So we've got 2 times 3 plus 4 times 0, 6 plus 0. We have a value of 6 there. And our last point at 3, 5. We've got 2 times 3 plus 4 times 5. 6 plus 20 gives us a value of 26. In this case, we have a bounded region, which means it's enclosed in all directions. It's not going to continue on forever. It's enclosed, which means we're going to have a min value and a max value. the way you find that is you look, we had 3 vertices, we look at our 3 points. We've got 12, 6, 26. The maximum value is the highest number. So we have a maximum value of 26, and that is going to come at 3, 5. And then our minimum value is 6, and that comes at 3, 0. So your max value is just the highest number that you find when you plug it into your objective function, and the minimum is the smallest value that you find when you plug into your objective function. All right, let's do one more example. What I want you to do here is step 1 is find that feasible region. So what I want you to do is press pause, and I want you to graph all 4 of your constraints and see if you can find the feasible region. What is the solution to that system of inequalities? Once you're done, press play and see how you did. All right, let's see how you did. We had a vertical line at 0, a horizontal line at 1. When we solved our third equation, we had our y-intercept of 3, slope of -3, 1. And then our last line, our pink line, once we solve, they were all solid lines. The hardest part is we went to the right of blue, so now we're only looking at the right hand side. We went above red, so now we're looking at this one little square. We went above green, so we went over here to green, and we went above pink. So this one's a little bit harder. You really got to consider all 4 of your equations. When it has this kind of graph, sometimes I'll go through and I'll really outline my region so I know exactly what part I'm looking at. Once I do that, I see that I have a vertex right here, a point at 0, 8. The next sharp point that I get to, the next vertex that I get to, is right here, which is at 2, 2. And then we follow our line over, and our next vertex is going to be at 4, 1. And then it follows over and it continues forever. So this is what we would have considered an unbounded graph. It's not enclosed. It's going to continue up here. So now what we need to do is use our 3 points and plug it into your objective function. What I want you to do again is press pause, plug your values into your objective function, which is right here, and see if you can find your min and max value. Alright, when you plugged in your first point of 08, you should have gotten 24. For 2, you should have gotten 10. And for 4, 1, you should have gotten 11. Hopefully, you did not fall into the trap I set up for you. This is an unbounded region, so you're not going to have a min and a max. You're only going to have one or the other. From this way, it looks like my unbounded region is going to forever continue to go up. But just to make sure, I'm going to pick a point up there of 10, 10. And I'm going to plug that in. And I want to see if it's going to continue going up so that I don't have a max. So I've got 2 times 10 plus 3 times 10, 20 plus 50, 20 plus 30 gives me a value of 50. So if I were to plug in my numbers continuously, I would never get a smaller number. It would continue growing up and up and up. Therefore, I do not have a maximum. But I will have a minimum. I will have one or the other. So when I look through, I've got a 24, a 10, and 11. So in this case, my minimum value is 10. Alright, so I know linear programming is a much more difficult concept. Just remember your 3 steps. We start with our constraints, which is just simply solving or graphing a system of inequalities. The hard part is finding that feasible region that's going to satisfy all the conditions. Once you have that, really trace through, find your coordinates of your points, which are all your vertices, anytime you come to a sharp point. Then when you are finding the coordinates, it's very important that you are accurately labeling the coordinates. A lot of times people will take this red line and say 4, 0 because they think it's an axis. Really pay attention and be careful with the points that you are labeling. Plug them into the objective function. If it is bounded, you will have a max and a min. If it is unbounded, you will have one or the other. Okay? And that is for linear programming today. You are all done.